This was filmed in front of a live studio audience. All right, let's talk about magnetic forces in fields with long straight wires. What does that mean? If I've got two wires and I put them next to each other, how are they going to interact? Both of them are going to create a magnetic field, so how do their magnetic fields interact between each other? Well, first thing we need to know is how do we calculate a magnetic field? Well, we got this cool little mu naught, aka the vacuum permittivity. No, permeability. Permittivity is a different thing. What does it mean? It doesn't matter. It has something to do with the geometry of space-time that is beyond the scope of this course. Just know that it's 4 pi times 10 to the minus 7 Tesla meters per amp. What is that unit? I don't know. It just makes stuff work. It's because of the fact that our units are not necessarily natural, so we just do our best to make it work with constants. Then you divide it by 2 pi r, where r is the distance between, or I guess the distance from the wire. We'll see between wires when we get two of them. But basically the two things that you're looking at is stronger current, stronger magnetic field, further from the wire, weaker magnetic field. Good so far? So let's try this out in a problem. I've got a wire, gotta have all my words there, a wire that goes up a building with a current of 25 amps. And I want to know what is the magnetic field 10 centimeters to the left of the wire. So what's this going to look like? Well, I'll draw my wire. There's my wire. It's got a current, 25 amps. I want to know what's the magnetic field over here, 10 centimeters to the left. Well, I'm going to need to know my magnetic field. I'm going to need to know magnitude and direction. How do we find magnitude? Right here. So I'll come over. B equals mu naught I over 2 pi r. Plug in my numbers here. So that's going to be 4 pi times 10 to the minus 7 times 25 amps. And this is Tesla meters per amp. On the bottom, we've got 2 pi and 0.10 meters. Cool beans, when we plug all that in, I get a magnetic field strength of 5 times 10 to the minus 5 Tesla, which just happens to be Earth's magnetic field strength, or approximately that. But I'm not done with the problem, because now I need to solve what's the direction of the current. Well, I'm going to have to use the right-hand rule for this. Thumb goes with the current, so it's up, and then I look at how my fingers curl. On the left side of my thumb, my fingers are sticking out of the page. So what that tells me is my magnetic field over here is coming out of the page. Remember, dot means out. It's like the arrow's being shot at you. X means in. It's like you're looking at the back of an arrow being shot. It's the fletchings of the arrow. Cool beans? So my final answer would be 5 times 10 to the negative 5 Tesla out of page or board or whatever you happen to be writing on. Cool beans? Cool. Now, magnetic field is a vector, so you have to add them with direction. What I want you guys to do right here, and you can try it on your own, I've got two different wires. I've got one with a current coming out of the page with 5 amps of current, and then I've got one going into the page with a current of 7 amps of current. They are 20 centimeters apart. I want you to try two things. One, figure out what it is at the center. What is the magnetic field at the center? And the second one is, what is it when it's 5 centimeters or 3/4 of the way towards this guy? Hey, take a look at this. Let's check it out. So on this first one here, since it is, both of them are exactly 10 centimeters from the center, so I put the same distance, though this one is 5 amps, this one's 7 amps. When I look at the direction of the current, though, because that's going to be important with them being vectors, this one is sticking out of the page. This one is going into the page. So I look, curl my hands, going up on this one, and then for this one going into the page, oh look, it's going up on this side. So they're both going to be up, adding on to each other. Hey, that's pretty neat. So I get 1 times 10 to the minus 5th, 1.4 times 10 to the minus 5th, straight add them up since they're both going up, and I get 2.4 times 10 to the minus 5th. Similar idea down here. The only difference is now I'm going to be changing my distance. So this one would be 5 centimeters, whereas this one over here, I'm going to have to calculate it for 15 centimeters. That's math. And then still just straight add them up because they're both going to be pointing up no matter what. Now, if I were to change this one's direction so that it's coming out of the page, then the only difference is I would have to subtract this because it would be going down. If this one's also coming out of the page, that means it's going down on this side. So that's the only difference that we're going to look at. Now that we have the idea for how to calculate the strength of magnetic fields, let's take a look down here for what the force is going to be. If you guys remember from the section on calculating the force on a wire that's carrying current, it's ILB, inside linebacker. That's the way I remember it. But now we know how to calculate the strength of the magnetic field, because when we have two wires, the only other thing that's putting a force on it is the other wire. What's creating the force? That magnetic field. So we plug in for B, this over here. This is the I of wire 1. This is the I of the one generating the magnetic field. So the force on a wire is just going to be these two equations combined. Note, this is not on your formula sheet. Both of these are, this guy is not. They expect you to be able to put them together on a test. So you can either remember it or you can just come up with it on the fly. Now, the thing you need to notice is the sign of this is going to determine whether it's attractive or repulsive. In this case, if both of my currents are going the same way, is it going to be attractive or repulsive? Well, let's take a look. Opposite sides of a magnet attract. If I'm going up, my magnetic field curls this way. That means I'm going into the board here, out of the board there. That's opposite sides of a magnet. It's going to be attractive. So when they go the same way, they're going to be attracted to each other. When they go opposite ways, now they have both sides of the magnetic field pointing the same way. They're going to be repulsive. So if you end up with a positive value for this, then it means it's attractive. Negative value means they're going in opposite directions. They're going to be repulsive.